Okay, ma? So, the next topic which we are studying is elasticity. Okay, small topic, easy topic. If possible, you will get one question from this one. Okay, ma? So, see, ma, what is meant by elasticity? Elasticity means ability of body to regain its original shape and size, okay, ma? After removing the deforming forces. After removing the deforming forces is called as elasticity. Okay, ma? So when you remove the forces which you are acting on a body, then the body will try to regain its original shape and size. So how good it is able to retain its original shape and size, that is called as elasticity of a body. Are you able to understand, ma? For example, if you take steel and if you take rubber, okay, ma? So out of them, which one do you consider is more elastic? Huh? Steel is considered more elastic. Okay, ma? Why steel is considered more elastic? Because you cannot easily elongate this steel. Okay? It means once you start elongating this steel, the restoring forces which develops between the molecules, it is very large. You are not able to elongate. What is the reason? Because intermolecular forces immediately come into action. No? So the intermolecular forces developing in rubber is very less. That is why you are able to easily elongate that one. Okay? But the intermolecular forces or interatomic forces existing between the molecules of steel, this is very large. Okay? So easily you cannot elongate it. So therefore, steel is considered to be more elastic when compared to rubber. Stretching property is not called elasticity. Are you able to understand, ma? Stretching property is not called elasticity. The ability to develop intermolecular forces is called as elasticity. Are you able to understand? Now let us study about, first of all, what is the reason for elasticity. Okay, ma? Reason for elasticity. Why elasticity comes into action. Okay. So reason for elasticity is intermolecular and interatomic forces. Okay. So these forces are responsible for the property called elasticity. Now let us try to understand. Sima. For example, if you take a rod, in this rod, molecules will be present, atoms or molecules will be present inside a rod. Okay? And if you don't apply any force on this rod, you are not applying any force. So, force applied on the rod is zero. Okay? Then if you take any two molecules, for example, if you take this one atom and this one atom, or two different molecules or two different atoms, anything. Okay? Then they are always present at their mean distance. They are present at a distance which is called as mean distance. Okay? And this mean distance is called as R0. Okay? So they are present at a particular distance when you don't apply any force. You are not compressing the molecules, you are not elongating the molecules also. Then they are present at a particular distance which is called mean distance. Okay, ma? Now what I do is, on these two molecules, I will apply compressing forces. These are the external forces which I am making to act on these atoms or molecules. So what is the direction of these external forces? They are compressing, no? Okay, ma? And these molecules, they doesn't want to change their mean distance. They want to be present at their mean distance only. They don't want to change their mean distance. So what they do is, they develop some repulsive forces. Okay, ma? So that these external forces, they are opposed. Okay, ma? So what these molecules will do? They will develop repulsive forces. Are you able to understand? Is it clear, ma? Similarly, now if I take the same two molecules, okay, which are present at a mean distance, and I try to separate them, I am applying external forces in this direction. Okay, I am trying to separate them. But they don't want to separate also. Are you able to understand what is happening? In the first case, I am trying to compress them. They will oppose compression. Second condition, I am trying to elongate them. That elongation also they will oppose. Okay. So what is the method of opposing these external forces now? ఇక్కడ మెథడ్ ఆఫ్ అపోజిషన్ వచ్చేసి డెవలపింగ్ రిపల్సివ్ ఫోర్సెస్, అక్కడ డెవలపింగ్ అట్రాక్టివ్ ఫోర్సెస్. ఓకేమా, దీస్ మాలిక్యూల్స్ దే స్టార్ట్ అట్రాక్టింగ్ విత్ ఈచ్ అదర్. ఓకే, अच्छा राइट, क्लास चलता है बच्चा. ओके माँ, सो ये कौन तो सता सकते रहे. ओके माँ, so they will develop attractive forces. Clear? So therefore these intermolecular forces, what they are doing, can you say? ఏం చేస్తున్నాయి? They are opposing the forces, whatever may be the forces, either attractive forces or repulsive forces. If you try to elongate these molecules, if you try to increase the distance between them, they will oppose. If you try to reduce the distance between them, then also they will oppose only. So repulsive forces, these intermolecular forces, they will only oppose the external forces. Are you able to understand? If you try to compress them, they will not allow compression. If you try to elongate them, they will not allow elongation. It means these intermolecular forces, just they are behaving like a spring which is present between two molecules. Are you able to understand, ma? See, for example, okay ma, if I take a spring, okay, so these are two bodies, and let two bodies, they are connected by a spring. Are you able to understand, ma? So if I try to compress this spring, what happens? If I try to compress this spring, what happens, ma? What happens? The length of spring reduces, no? And if the length of the string reduces, these restoring forces will develop in which direction? Restoring forces will develop in opposite direction. These are the restoring forces direction, Fr. Clear, no? Similarly, if I take two molecules or two bodies, okay, ma, and I am trying to elongate this spring, these are the direction of external forces. Then what restoring forces will do? Restoring forces will develop forces in exactly opposite direction. This is what happens in the case of a spring normal. Same condition is existing in the case of two molecules also. Okay, so therefore what we write, therefore the note point which we have to write is, okay ma, so intermolecular forces always oppose external forces. Okay ma, this is the reason for elasticity. Okay, so reason for elasticity, I hope you have understood, no ma. For example, this is a pen. Okay ma, if I try to increase the length of this pen, is it possible very easily? No. Why? Immediately intermolecular forces, they start developing attractive forces. Similarly, if I try to compress this spring, then the molecules will develop repulsive forces. It means the molecules of this pen also, they are behaving just like as if springs are present in between them. Just how springs behave, intermolecular forces also behave in the same sense. Are you able to understand? So what are the formulae we can apply in the case of springs? All the formulae we can apply in the case of these atoms and molecules also. Okay, so if you study in advanced level, you will get questions just like questions in the case of springs also. In the case of elasticity also. Okay, that's it. Okay, ma. Now let us see about the types of deforming forces. How many types of deforming forces we have? Okay, so types of deforming forces. What is meant by deforming forces, ma? Deforming forces means what? The forces which are responsible for changing the size, shape, volume of a body, they are called as deforming forces. Okay, so first one is called longitudinal force. Longitudinal force. It means, for example, this is a rod which is fixed here, and if I apply this force, what happens to the length of the rod? Length of the rod increases by, this is L, this is small l, or you can call it as delta L also. Are you able to understand? Length of the rod increased, no? So this type of force which is making the rod to expand or to increase in length, that is called as longitudinal force. The force is perpendicular to the contact surface. Are you able to understand? So here I can say force is perpendicular to contact surface. Okay, which is the contact surface here? This is the contact surface. No? To this contact surface, force is in which direction? It is acting at an angle of 90 degrees. Okay, so the second type of force, which is called as normal force. Normal force. So what is meant by normal force? For example, if I take a football, okay, and if I apply force at an angle of 90 degrees in every direction, okay, I am applying force at an angle of 90 degrees in every direction. Then what happens to the size of this football? Size of this football reduces, no? Size of this football reduces. So here also, this type of force is responsible for to reduce the volume of this football. So this is another kind of force which is responsible for reducing volume of a body. Clear, ma? One more type of force which is possible is shearing force. Okay, ma? Third type of force is called shearing force. Okay. So what is meant by shearing force? See, ma. For example, if I take a box and this box is fixed to the ground. Okay, ma? Box is fixed to the ground. So if I apply a force in this direction, so this is what kind of force? This is a tangential force. Tangential force. See, ma, these two forces, they were perpendicular forces, no? But this force is a tangential force. It is a tangential to the topmost surface. Are you able to understand? Then what happens to this body, ma? Base of the body, you are fixing it. Idi move out on lead. Only top of the body, I am applying force on this body. Then what can happen? So this body will bend, no? This body will bend like this. Okay? So if you are responsible for changing the shape of the body, that type of force is called as shearing force. Are you able to understand, no? So these are the different types of forces which we have to study in the case of this elasticity. Okay? So next we study about stress. What is meant by stress? Force per unit area. Okay, ma? Force per unit area is called as stress. This you can call it as pressure also. Okay, ma? Because force per unit area is nothing but pressure only, no, ma? So therefore stress is nothing but how much force you are applying and how much area of a surface. Okay? For example, here if I want to calculate a stress, so you take this force and you take the area of cross section. Here we will have some area of cross section, no, ma? So that area of cross section, if I divide, then it is called as a stress. Understood, no? So here also, if I take the total force which is acting divided by surface area. Surface area of a football, 4 pi r square, no, ma? Okay? So force per surface area, this you can call it as stress in this condition. Are you able to understand, ma? So this is also called as stress. Okay? Now here how can I calculate a stress? Force divided by the topmost area will be there, no, for this body. Topmost area. This area is called as A here. Which area we are supposed to take? We are not supposed to take the area of this side. We are not supposed to take area of the perpendicular side. We are supposed to take area of the topmost surface on which we are applying force at an angle of 0 degrees. Are you able to understand, ma? Because this is what kind of force? Tangential force. So this area you have to take. So students will be confused here, ma. While solving the problems, class చెప్పేటప్పుడు ఏదో లోకంలో ఉంటాయి ఏరియా అంటే ఏరియా ఏదైతే ఉందన్నట్టు ఉంటారనమాట. ప్రాబ్లమ్స్ చేసేటప్పుడు తెలుస్తుంది ఈ ఏరియానా ఇదే ఏది తీసుకోవాలబ్బా అని. ఈ టాప్ మోస్ట్ ఏరియా తీసుకోవాలి. Are you able to understand? So therefore stress is nothing but force per unit area, and depending on different conditions you have to take the areas of the bodies. Okay? Then we define another term which is called as strain. Okay? What is meant by strain? Okay, ma? So change in length, or you can say change in dimension to original dimension. Change in dimension to original dimension is called as strain of a body. Okay? So strain is a dimensionless quantity, you know. Stress has a dimension. Stress dimension is dimension of pressure only. Okay, ma? But what is strain? Strain is a ratio. Change in dimension to original dimension, or you can say change in length to original length, change in volume to original volume. So on the numerator also you have length, denominator also length. In numerator also you have volume, denominator also you have volume only. So therefore strain is a dimensionless quantity. It does not have any dimension. Okay, ma? So therefore write down, it is what kind of quantity, ma? It is a dimensionless quantity. Okay? It does not have any dimension. This is about strain. Okay? So therefore, how many types of forces are there? three types of forces we are studying. So therefore, three types of stresses will be there and three types of strain also will be present. Are you able to understand? So stresses any rakalu? Mood rakalu. Strains, three types. Forces, how many types? Three types. Okay. So these three types we are going to study here. Completed, ma? So therefore, what we write? Okay. So we will study some more detail about a strain only, ma. See, ma, strain. So, for example, this is a rod. Okay, ma? And by applying some force, length of the rod has increased. Okay. So this is a delta L and this is L. Okay. Then how can you define a strain here? Strain is nothing but delta L divided by L. This is called as strain. Or you can call it as longitudinal strain. Okay, ma? This also you can call it as longitudinal strain. Okay. So then second type of strain is, for example, if you take a football and you are applying forces in every direction. Okay, ma? Then what happens to the volume of this football? Volume of this football reduces. So this is called as normal strain, or you can call it as volumetric strain. Volumetric strain. So which you can write delta V divided by V. Delta V is nothing but change in volume to original volume, volumetric strain. Clear, ma? Second type of strain. One more type of strain is SEMA. So this is a body which is fixed to the ground, okay, and we are applying some tangential force. Okay. Then what happens to the shape of this body? Shape of this body reduces. Shape becomes like this. Okay. So here, stress. Stress, how can I define? So here we have some topmost area, no ma? This is A. So force per unit area. Okay. And strain, how can I define? Strain is nothing but, see ma, top surface, this should have moved by this much of length, no? This is delta L. What is delta L here? The length which is moved by the top surface, that is delta L. And here, this side surface is there, no? This length is called L. So here strain is defined as delta L divided by L. This is strain here. Are you able to understand, ma? So if you apply force on the topmost surface will move in a straight line by some distance, no, ma? That distance is called delta L, and this perpendicular length is called L. So delta L by L is called as strain in this condition. See, ma, here also we are writing delta L by L. Here also we are writing delta L by L. But this delta L by L and this delta L by L, they are not same. Okay. So this is elongation per original length. This is lateral moment of the topmost surface divided by perpendicular distance. This formula and this formula, both of them, they are not same. Okay. So therefore, we have studied three types of stresses, three types of strains. Okay. So therefore, now we study a very important parameter which is called as modulus of elasticity. Okay, ma? Modulus of elasticity. Okay. So modulus of elasticity is nothing but stress divided by strain. Okay. The ratio of stress and strain is nothing but modulus of elasticity. So how many stresses? 3. How many strains? 3. So how many modulus of elasticities? 3. 3 modulus of elasticities. Abba. ఫోటోలు తీసి పెట్టుకోవాలరా క్లాస్కి వస్తానే ఫస్ట్ నమస్కారం చేసి ఓకేమా. సో వీ హ్యావ్ 3 types of moduli of elasticity. Modulus is singular form, moduli is plural form. Okay. So therefore, what is the first modulus? First modulus is called as Young's modulus of elasticity. Okay, ma? Young's modulus of elasticity. Which is represented by capital Y. Capital Y means Young's modulus of elasticity. named after the name of the scientist Thomas Young. Okay? But he became old man also, ma. His name was Young, that's all. Okay? Alright? See, ma. So therefore, Young's modulus of elasticity. What is Young's modulus of elasticity? Okay, ma? So that is equals to longitudinal stress divided by longitudinal strain. Okay, ma? So longitudinal stress, first of all, we will calculate longitudinal strain is how much? Delta L by L, no, ma? Strain is what? A change in dimension to original dimension. So longitudinal stress is nothing but force per unit area, no? Force is F, and this has an area of A. A means area of cross section here. Area of cross section is A. So longitudinal stress divided by longitudinal strain. So longitudinal stress is nothing but force per unit area, no, ma? And longitudinal strain is how much? Delta L by L. So therefore, if I manipulate this one, then I will get F into L by A into delta L. So this is the equation to calculate what? The Young's modulus of a rod. Okay, ma? So for this rod, which rod? This rod. This is the equation to calculate Young's modulus. F into L by A into delta L. Are you able to understand, ma? So first of all, we forgot to study about Hooke's law, ma. By Hooke's law only, actually, we have to derive this modulus of elasticity. Okay? Completed? Make a note up to here. Actually, why we got this modulus of elasticity, let us see. Okay? We have to study about a law which is called as Hooke's law. Hooke's law. What is Hooke's law? In springs already we have studied, Nama. For example, if this is a spring of a spring constant K. Okay? So if I apply, this is the main position of the spring. Okay, ma? And by applying some force, if I try to elongate this spring by a distance of x, by applying an external force of F, then spring will develop a restoring force, no? Spring will develop a restoring force. And this restoring force is directly proportional to minus x. This is called as Hooke's law, no? Do you remember? So if you elongate a spring in this direction, restoring force develops in opposite direction. And that restoring force is directly proportional to negative of x. It means if elongation is greater, you have to apply more external force, and if external force is more, restoring force is also more. Okay, ma? Similarly, in the case of elasticity also, we study Hooke's law. So here restoring force is directly proportional to x, no, ma? And in the topic of elasticity, okay, ma? In the topic of elasticity, we write stress is directly proportional to strain. This is called as Hooke's law in elasticity. Okay, ma? In the case of springs, restoring force is directly proportional to minus x. But in the case of elasticity, stress is directly proportional to strain. Okay? And this stress by strain ratio, stress divided by strain ratio, this is a constant, no? Okay, ma? If a stress is directly proportional to strain, stress by strain should be constant. And that constant is nothing but modulus of elasticity. Okay, ma? That is nothing but modulus of elasticity. Are you able to understand how I got this modulus of elasticity? Just it is the ratio of stress by strain, which is a constant. Are you able to understand, ma? And because there are 3 types of stresses and 3 types of strains, modulus of elasticity is also 3 types. That's it. Is it clear? Right. Okay. So therefore we were studying about Young's modulus of elasticity, which can be written as longitudinal stress by longitudinal strain. So longitudinal stress, force per unit area, applied force per unit area. Strain is nothing but change in dimension to original dimension. Which dimension is changing here? Length is changing, no? So delta L by L. Are you able to understand? So stress has a dimension, ma? Strain does not have a dimension. So F into L by A into delta L. Are you able to understand? Right. So next we study about a very important graph which is called as stress-strain graph, on which theoretical questions can be asked. Okay. So draw the next, keep the next side heading which is called stress-strain graph. Stress-strain graph. So previously sometimes questions were asked on these graphs. Okay, now let us. So, first of all, let us try to understand how we will draw these graphs. See here. First of all, I will take a rod. Okay, ma? And on this rod, I will attach a pan to this rod on which I can place some masses. Understood, ma? So first I will place 1 kg mass. Then this rod will elongate by some distance. No? Okay, ma? If I place a small body, elongation will be smaller. If I get elongation, I can calculate strain also. No? Stress is nothing but force per unit area. Force is nothing but weight of this body. Are you able to understand? Stress is nothing but force per unit area. Strain is nothing but elongation to original length. Okay, ma? Then if I add some more mass, then what will happen? Further elongation will be there. So strain is changing, stress is also changing. Or you can say stress is changing, strain is also changing. So therefore, continuously I will increase the masses and I will measure the elongation which is produced in this rod. And by taking both of them, if I draw a graph, okay, ma? Where on y-axis I am taking stress, on x-axis I am taking strain. Okay. So for different materials, this graph will be different. Ma? For example, if I write for any one body, then graph will be approximately like this. Okay. Like this. So let us call this point as, let us draw some more good graph. Ikkada raadu. Here you will not get a straight graph. That is the importance of this graph. See, ma? So this point is called as point A. This point is called as point B. This point is called as point C. And this point is called as point D. These are the 4 points. And questions can be asked on these points. And questions can be asked on slope of the graph also. Okay? Now let us try to understand what is the meaning of this graph. So graph is between which one and which one, ma? Stress and strain. Stress is nothing but force per unit area. Strain is nothing but delta L by L. You are continuously increasing force, no? Okay, ma? So what happens to elongation? Elongation also will increase. So stress is increasing, strain also will increase. And this point A is called as proportionality limit. Proportionality limit. Why do you call it as proportionality limit? Anybody, can you say? Up to point A, that point is called as proportionality limit. Proportionality, see, up to this point O to point A, graph is a straight line. From this point, from the origin to point A, graph is a straight line. Graph is a straight line means what? This is the position where I can say stress is directly proportional to strain. Okay? It means up to this point, graph is a straight line. It means up to point A, the rod is following Hooke's law. Rod A rule ni follow chestundi, it is following Hooke's law. That is, stress is directly proportional to strain. Okay? So therefore, up to this point, rod is following Hooke's law. Okay, ma? And what is meant by Hooke's law? Stress is directly proportional to strain. Okay. Are you able to understand? So what is the ratio in which stress is increasing? In the same ratio, strain is also increasing. So therefore, graph is a straight line. Okay, ma? So only up to point A only Hooke's law is satisfied. After that, Hooke's law is not satisfied. Okay, now see. Now after reaching up to point A, if I start unloading these masses, okay, ma? After reaching up to point A, continuously I was placing masses, no, so that stress increases. Now I am unloading the masses. Okokka mass ni teesestu unnanu. Then can you say what happens? Stress decreases. Because stress is decreasing, strain also decreases. So graph will be retraced exactly in opposite direction. Are you able to understand? For 1 kg weight which you have placed, elongation is 1 centimeter. If you place a 2 kg body, elongation is 2 centimeter. You are placing 3 kg body, elongation is 3 centimeter. Now you are removing 1 kg body, elongation also reduces. Ante the wire is able to regain its original size and shape. You remove 2 kg, again length decreases. You remove all the masses, wire will reach to its original shape and size. Are you able to understand? So therefore, here what is the importance of this point? If restoring forces are removed, sorry, not restoring forces. If external forces are removed, here what are the external forces, ma? These masses, they are nothing but external forces. If external forces are removed, wire or rod regains its original length. Okay, ma? It will regain its original length. That is, it will regain its original shape and size. Are you able to understand? Okay. Now, next point is called as point B, which is called as elastic limit. Elastic limit. Okay, ma? Up to point A, it is clear now what is happening there. Now we are studying about point B. And what is the name of this point? Elastic limit. Why we are calling this one as elastic limit? Because at point B, here also if you remove the restoring forces, again the wire will regain its original shape and size. But here, in between A and B, Hooke's law is not satisfied. A ki B ki madhyalo, Hooke's law satisfy avvatam ledhu. Why Hooke's law is not satisfied? Because graph is not a straight line. Graph will be a straight line only when stress is directly proportional to strain. But after reaching to point B also, further if you remove these masses, again wire will regain its original shape and size. Are you able to understand, ma? So therefore, at B, if restoring forces are removed, rod will gain its original length. Okay, ma? That is why it is called as the limit of elasticity of a body, which is called elastic limit. Are you able to understand? Next point is called as point C. Okay, ma? And now from A to B, you write one point, ma. From A to B, Hooke's law is not satisfied. That also you write down. So from A to B, Hooke's law is not satisfied. Hooke's law is not at all satisfied in this region from A to B. Okay, ma? So next one is, we study about point C. And point C is called as yield point. Okay, ma? Point C is called what? It is called as yield point. Now can you say what is meant by yielding, ma? Yielding means what? Yielding means giving something is called yielding, no? So here yielding means what? At a point C, after reaching point C, if you remove the deforming forces, body will regain its original length only up to some extent. Total length cannot be regained. It means there is some permanent elongation in the rod. Are you able to understand? So, for example, let elongation is 5 millimeters now. Total rod has elongated by how much millimeters? 5 millimeters. Ante rod lo perigina length yanta, length of the rod has increased by 5 centimeters. That is called as a delta L, no? So after reaching to this position, now if you remove these masses, then wire will regain its original length, not totally, only up to certain extent. So instead of regaining total 5 millimeter, it will regain only 4 millimeter. It means there is some permanent elongation, no? How much permanent elongation is there? 1 mm. That is why it is called as yield point. అర్థమవుతుంది కదమ్మా? ఒక పర్టికులర్ మాస్ కన్నా ఎక్కువ మాస్ మీరు యాడ్ చేస్తే ఇంకా బాడీ తన ఒరిజినల్ లెంత్ని పూర్తిగా రీగెయిన్ చేయలేదు, కొంచెం పర్మనెంట్ ఎలాంగేషన్ ఉంటుందన్నమాట. ఓకే, దట్ ఈస్ కాల్డ్ యాజ్ yield point. Okay, so what is meant by yield point here? If restoring forces are, if external forces are removed, okay ma, body regains original length only up to 80 to 90%. Better we say in terms of percentages. Okay. So even after removing all deforming forces, even after removing all deforming forces, there will be some permanent elongation. There will be some permanent elongation in the rod. That is why this point is called as yield point. Okay, ma? Arthamavutundi kada? At point A, if I remove the deforming forces, definitely the body will regain its original length. At point B also, it will regain its original length. But at point C, this never regains its original length. Are you able to understand? That is the meaning of it. So next one, we study about point D. Now what is meant by point D, ma? If you go on adding the masses, at some point wire will break down, no? Okay? So that maximum weight up to which the wire doesn't break down, that is called as point D, and it is called as ultimate breaking strength of the wire. Okay, ma? ఒక పర్టికులర్ పొజిషన్ దగ్గర ఇంకా మీకు ఒక లిమిట్ కన్నా ఎక్కువ మాసెస్ ప్లేస్ చేస్తూనే ఉన్నారు, తెగిపోతుంది కదా. సో తెగిపోయే ముందు అది ఎంత బరువునైతే బేర్ చేయగలదో దాన్ని మనము అల్టిమేట్ బ్రేకింగ్ స్ట్రెంగ్త్ ఆఫ్ ద వైర్ అని అంటాం. ఇస్ ఇట్ క్లియర్? సో రైట్. సో నెక్స్ట్ వన్ ఈజ్ పాయింట్ డి. Shall I write here? Point D. So what is meant by point D? It is called as ultimate breaking strength. Ultimate breaking strength of wire or rod. Okay, ma? Is it clear? It means it is the maximum weight a wire or a rod can bear. After that, it will break down. Clear, nama? So questions will be asked on these 4 points, ma. So be careful. Make a note up to here. Okay, ma. So next we study about types of materials. Types of materials. We have studied only about Young's modulus, nama. Remaining 2 moduli we will study after discussing this one. Types of materials. So materials may be ductile. Okay, ma? Materials may be brittle. 2 types of materials we can say them. Ductile materials means what? So you can increase their length, you can increase their volume, you can change their shape very easily and by a very large factor. For example, if you take a very small rod of gold, gold is a very, very ductile material. So if you take a small piece of gold, you can spread it up to 20 to 30 meters also. చిన్న అంత ఐరన్ రాడ్ తీసుకొని 34 మీటర్లు దాన్ని సాగదీయచ్చు మీరు, బట్ స్టిల్ ఇట్ డజంట్ బ్రేక్ డౌన్. ఓకే, దట్ నేచర్ ఈస్ కాల్డ్ వాట్? దట్ నేచర్ ఈస్ కాల్డ్ ductile nature. And some materials, they break down very easily without elongation. For example, a piece of chalk piece. Chalk piece, you should have seen a white color chalk piece. If you try to elongate it, will it elongate? It will break down. So such material is called brittle material. Glass, chalk pieces, mud, these are brittle materials. Are you able to understand, ma? So ductile nature means what? They can be elongated by large length. Okay, ma? Brittle means they break down when deforming forces are applied. Break down when deforming forces are applied. Okay, so here you can say ductile materials mean the delta L, delta V will be large. Change in length, change in volume, they will be very large. But brittle material means delta L, delta V, they will be very, very small. Such materials you can call them as brittle materials. Are you able to understand? For example, if you take a rubber band, you can elongate it to very large length, no? Are you able to understand? Why? Why you can elongate to a large length? Because it is a ductile material. Okay? And a piece of chalk or a piece of glass, they break down if you try to apply force on them. That is why they are called as brittle materials. Understood, no? And by looking at the shape of this graph, we can identify whether a material is a ductile material or a brittle material. We can say whether it is highly elastic material or it is not highly elastic material. All these properties we can define by looking at the graph. Okay, let us see some example graphs which can be asked in the examination. Okay, ma? So I take 2 graphs, ma. First example I am taking. Okay, so this is a stress and this is strain. Okay, so first graph is This is a first graph and this is a second graph. Okay. So one of them is steel and one of them is rubber. Now can you say which graph is for steel and which graph is for rubber? Huh? Naming. 1, 2. Which graph indicates the stress strain graph of steel and which one is for rubber? First one is steel, this one. How can you say? This one you are saying steel. How can you say? Second one is steel. How can you say? ఈ రెండు డైరెక్ట్లీ ప్రపోర్షనల్గానే ఉన్నాయి. Both the graphs are straight line only, no? Where? In first one, which is greater? Strain is greater. Sima, here in the first graph, okay, you are applying a lot of stress in the first graph, but the strain is very less. Are you able to understand? Winand carefully. For example, this is the amount of stress produced in first graph, and what is the amount of strain produced? This is the amount of strain produced. This is a strain, and this is stress for the first graph. Okay, so stress is very large. It means you are applying very large force, but elongation is very less. Okay, ma? And for the second one, how much is the stress? Only this much amount is the stress. This is the stress. And but what is the strain? Strain is very large. Clear, no? It means that definitely first graph belongs to steel, second graph belongs to rubber. Are you able to understand? So you have to take the comparisons of stress and strain. Okay? Stress means force applied per unit area. It means you are applying very huge area, a very huge force. Strain means what? Elongation of the body compared to original length of the body. So strain represents elongation. Stress represents the force which you have applied. Okay? Understood now what is happening? So in the first graph, what is happening? Okay, ma? Stress is large, strain is less. That's all, no, ma? Stress greater means what? Applied force is very large. That is the meaning of this one, no? Because stress is nothing but force per unit area. Strain is less means what? Strain is nothing but delta L by L, no, ma? It means delta L is very small. It means you are applying great force, but elongation is very less. It means first graph should be graph of a steel. So therefore, if you take a modulus of elasticity for both the bodies, okay. So if I take modulus of elasticity of steel, okay, ma? So this is equal to stress divided by strain. Modulus of elasticity, this is the formula, no, ma? Stress by strain. And modulus of elasticity of rubber, this is also, what is the formula? This is also stress by strain. Are you able to understand? So out of these two moduli, which one is greater? For steel is it greater or for rubber? Steel, because stress is very large, strain is very less. So modulus of elasticity of steel, it is very large when compared to modulus of elasticity of rubber. That is why we say steel is more elastic when compared to rubber. Are you able to understand, ma? Therefore we say steel, or we can write like this: modulus of elasticity of steel is greater than modulus of elasticity of rubber. ఇది గ్రేటర్ దాన్ సింబల్ ఏందో అనుకుంటారు మీరు, ఏందో కప్ వేసినాడు చాలా ఐస్ క్రీమ్ తాగుదాం దాంట్లో అనుకుంటారు. Greater than symbol. Clear, ma? So therefore elasticity of steel is greater than elasticity of rubber. Understood, ma? So if modulus of elasticity is greater, it means it is a more elastic material when compared to other materials. That is the meaning of this one. Okay, completed, no? Similarly, if I draw one more graph, okay, if I draw one more graph, Sima. So out of these two materials, which one is a ductile material, which is a brittle material? So first one is a brittle material. Clear number? And second one is a ductile material. What is the reason? So therefore, what can we say? So if distance between A and D is very small, it means, for example, this is a stress and this is a strain number. So distance of a strain is very less. This is very less. It means the material will break down very easily. Okay. Whereas if you see this distance, so here strain is very large. It means the elongation can be very large. So ductile material, and this one is a brittle material. Okay. So right now. So after that, we study the next modulus of elasticity, which is called bulk modulus. Okay, ma? First one we have studied Young's modulus, no? Now the second modulus of elasticity is called bulk modulus. Red color pen ekkada? Oh. Bulk modulus. Okay. So bulk modulus you can represent by K, you can represent by B. And according to the books, this representation will change. We better represent by B. B means bulk modulus. Okay. So what is meant by bulk modulus? See, for example, this is a football. Okay. We are taking this football to a depth of 1 kilometer inside water. This football, I am taking this one to a depth of 1000 meters inside water. At 1000 meter depth, there will be lot of pressure, no? Water applies very huge amount of pressure. For every 10 meters, water applies a pressure of 1 atmospheric pressure. So 1 kilometer means the pressure will be very, very large. Human beings, even they cannot breathe also. Even they have oxygen cylinders. Okay, ma? So therefore, at this much of depth, force will be applied in every direction, no? Okay, ma? Pressure will be acting on every side. So it means force is acting on every direction perpendicular to the surface of the football. So what happens to the size of the football? Size of the football reduces. Okay. So therefore, how can I write a bulk modulus, ma? Bulk modulus is nothing but normal stress divided by volumetric strain. Volumetric strain. Normal stress divided by volumetric strain. Normal stress is nothing but force per unit area. Volumetric strain is nothing but delta V by V. That's all, no? Change in volume to original volume of the body. Is it clear? So therefore, bulk modulus can also be written as F into V by A into delta V. This is called as bulk modulus. Are you able to understand? Same relation I can also write like this also. So F by A divided by delta V by V can be written as pressure divided by delta V by V. Okay, ma? So B can be written as I can write like this also, pressure divided by delta V by V. Or you can write pressure into volume divided by change in volume. You can write like this also. Are you able to understand me? This is called as bulk modulus. Bulk modulus means are able to understand what is happening? So what is the stress you are applying per what is the change in volume, fraction of change in volume, which is called as strain. That is called as bulk modulus. Clear now? Then we study about a third type of modulus, which is called rigidity modulus or shearing modulus. Okay, ma? Third type of modulus is rigidity modulus. Or shearing modulus. Okay, ma? So it can be represented by eta, or you can represent by R, anything. Okay. So what is meant by shearing modulus? For example, this is a box which is fixed to the base of any body. So here base is fixed. Base is fixed. Okay. Now topmost surface area is A. We are applying a tangential force of F. Length of this side is L. Okay. Then if I apply force on the topmost surface, this shears, no, shearing will happen. Shearing means topmost surface moves by this much distance. So this distance moved is called delta L, and this perpendicular distance is called as L. Okay. So here shearing modulus or eta, how I can write? So tangential stress divided by tangential strain. Clear? So tangential stress, how can I write? Tangential stress can be written as force per unit area divided by delta L by L. That's it. Okay, ma? So this is also of the form of F into L by A into delta L. Okay, ma? Young's modulus also we got same equation. Young's modulus also F into L by A into delta L only. Okay, but here L and delta L different, that L and delta L they are different. Okay, so here shearing stress we will take, there we will take longitudinal stress. Understood, no? The difference you should not forget. So these are the three types of moduli which we have in the case of elasticity. Understood, no, ma? Okay. Make a note. Okay, ma. So see. What happened? Okay. So the next concept is Poissons ratio. See, ma, here. So this is a rod, ma, whose original length is L. Okay, ma? Original length of the rod is L, or original length of the wire is L. Now we are applying some longitudinal force, ma. Then what is the elongation produced? This much is the elongation which is produced, you know. Okay. But whatever it may be, total volume of the rod should be a constant, you know. Total volume of the rod should be constant. Okay, ma? It means if length increases, diameter should reduce, no? Are you able to understand? Total volume of the rod you can never change, no, ma? Are you able to understand? So if length changes, what happens to the volume? Volume remains constant, diameter reduces. So therefore we write that if length of rod increases, what happens to diameter? Diameter may reduce. In every condition, diameter may not reduce. In some cases, diameter also may reduce. Okay. So therefore, first of all, we will study lateral strain. Lateral strain is nothing but delta D by D. Okay. So change in diameter to original diameter. Okay. So initially, a rod was having this much diameter, no? This is the diameter of the rod. Now diameter has reduced, no? That reduced diameter is called delta D. Okay. And one more strain, longitudinal strain. This is nothing but change in length by original length. Okay. Poissons ratio symbol andre sigma. Okay. Therefore, Poissons ratio sigma is represented by lateral strain divided by longitudinal strain. Okay. Or you can write as sigma is equals to delta D by D divided by delta L by L. This is called as sigma, Poissons ratio. Okay. The ratio of lateral strain to longitudinal strain. So delta L by L will be positive, but delta D by D will be negative. Why? Because diameter is finally reducing, no? Diameter is finally reducing if length increases. So therefore, sigma also we can write a negative of delta D by D by delta L by L. This ratio we can call it as Poissons ratio. Okay? Right. Okay. Sima. So next concept is strain energy. Sima, for this rod to elongate, we should do some work, no? Rod and elongate challenge, definitely we should do some work. Rod to elongate we have to do some work on the rod. So according to law of conservation of energy, the work which you do, it will be stored as some another form of energy, no? Energy you can convert into one form to another form. So the work which you do to elongate the rod, it will be stored as potential energy inside the rod. Okay, ma? And for that one, the formula is this one, half into F into delta L. Okay. F is the force which you are applying for elongating this rod. Okay, ma? And delta L or small l, it is called as elongation produced in the rod. Okay, this is one formula, and this formula we can manipulate this one into some different formulae also. Let us see. Okay, ma? So strain energy, or you can say potential energy stored in the rod. How can I write? Okay, ma? Delta U, change in potential energy. So half into F into small l. That's all, ma? So this one I will multiply by force per area multiplied by small l by capital L multiplied by A into L. Is it correct? Any problem? So A by A will get cancelled, no? L by L also will get cancelled. But what is F by A? Force per unit area is called stress. Delta L by L, strain. Area of cross section into length, volume. This is another formula which I got. Okay, ma? So total energy stored in the rod will be how much? Total energy stored in the rod is, this is one more formula. These formula are very, very important, ma, because many times direct questions will be asked in the examination. So half into stress into strain into volume. Okay. And sometimes question will be asked like this also. Energy stored in the rod per unit volume is how much? This is the total energy stored, no? And if I want to calculate energy stored per this much amount of rod, for unit volume of the rod, it means you just take volume to this side. Then what I will get? I will get half into stress multiplied by strain. Okay, ma? So this is another formula to calculate energy per unit volume of the rod. This is not total energy, ma, don't be confused. This is total energy. This one is total energy. This is also total energy. This is also total energy. Okay? But what is this? This is energy per volume of a rod. Per 1 centimeter cube volume, for 1 meter cube volume. What is the energy stored? That is half into stress into strain. Is it clear? Now from the same formulae, I will try to derive some more formulae, ma, which are asked many times in the previous exam. See, ma. So stress, how can I write? I can write Young's modulus into strain, no, ma? Stress can be written as Young's modulus into strain, because Young's modulus is nothing but a stress by strain. So substitute here. So energy per unit volume of a rod is nothing but half into, instead of stress I can write Young's modulus multiplied by strain, and again there is one more strain. So therefore what is the total formula? Half into Young's modulus into strain square. So this is another formula for energy per unit volume of a rod. Understood now? Similarly, strain, how can I write? Strain can be written as stress divided by Young's modulus. No? Again you substitute in the same formula. So energy per unit volume can be written as half into stress multiplied by, instead of strain what I can write? Stress divided by Young's modulus. So therefore half into stress square divided by Young's modulus. Clear now? This is one more formula which we can remember. And the question can be asked on any of these equations. Ivanni meeku brain lo undali. Are you able to understand? That's it. So one formula is half into F into small l, ma. Don't be confused. Small l is nothing but elongation. Small elongation also you can call it as delta L. And the total energy half into stress into strain into volume. Energy per unit volume half into stress into strain. Energy per unit volume half into strain square multiplied by Young's modulus. Energy per volume half into stress square divided by Young's modulus. These are the different